Hi students, welcome to the video lectures of software engineering. So in today's lecture, we'll talk about black box testing. So what is black box testing? And uh, we'll discuss the things. Okay, the black box testing, also called behavioral testing, focuses on functional requirements of the software. So black box testing enables the software engineer to derive sets of input conditions that will fully exercise all functional requirements of the program. Okay, so now black box testing, we also called it as behavioral testing. Okay, so in this method, we basically test the software's functionality without looking at the internal code. It's like, giving inputs to the program and checking whether the output is correct as per the requirements. So we need not know how the system is implemented. We only focus on the input and output behavior here. Okay. So next, black box testing attempts to find errors in the following categories. First one is incorrect or missing functions. Second is interface errors. Third is errors in data structures or external database access. Fourth is behavior or performance errors. Fifth is initialization and termination errors. Okay. For example, if a login system accepts wrong credentials without giving an error, so this is a functional error detected by our black box testing. Okay, so that's what we can understand from the above. That is, we try to uncover the errors in several important areas that is categorized as below. That is incorrect or missing functions and interface errors and mistakes in accessing databases or data structures, or performance related issues or errors in how the program starts or ends. Okay. Right, next, we talk about the graph-based testing methods. Okay. Now, we explore the graph-based testing. Okay. So, software testing begins by creating a graph of important objects and their relationships, and then devising a series of tests that will cover the graph so that each object and relationship is exercised and errors are uncovered. So, a graph is a collection of nodes that represent objects, links that represent the relationship between objects. So, node weights that describe the properties of a node, link weights that describe some characteristics of a link. Okay, simply to say, so we create a graph of how different components in the software are related, like objects and the links between them, which means, let me write here, nodes or objects, links equal to relationships, node weights is equal to properties of object. Okay. Link weight is nothing but what? Properties of relationships. Got the point? Right. So to illustrate this, let us consider an example. So in a social media application, so users are nodes and friendship is a link. So we test whether features work across these links properly or right. Okay. Next, we have graph notation. So you can see the example of graph notation between the objects, the directed link and undirected link and parallel links that exist. And below you can see attributes are mentioned. So new file menu select, where menu select generates the document window and the document text. Okay, it is represented with where the new file menu, document window, and document text, and the relationship between those. So the parallel link is existing between your document window and document text. Okay, directed link is in between new file menu select, where menu select generates the document window. Okay, so then we talk about equivalence partitioning. Okay, so equivalence partitioning is, it's kind of technique where we try to divide all the possible inputs into the partitions or classes. if one input from the class works, we assume the others will behave similarly. That's what equivalence partitioning is. So it is a black box testing method. So that divides the input domain of a program into classes of data from which tests can be derived. So test case design for equivalence partitioning is based on an evaluation of equivalence classes for an input condition. If a set of objects can be linked by relationships that are symmetric and transitive or reflexive, an equivalence class is present. An equivalence class represents a set of valid or invalid states for input conditions. So typically, an input condition is a specific numeric value, a range of values, a set of related values, or a Boolean condition. Okay. So the three main guidelines what we have to understand is, if the input is a range, test one valid and two invalid values. So if your input is a specific value, so again choose one valid and two invalid. So if input is a set, then we have to choose one value inside and one outside. Okay. Let us say, for example, if a form is accepting, if a form is having a parameter called as age, and the form is accepting the age only in between 18 to 60. Okay. So the valid class for this particular would be 30. So invalid classes are what? Anything out of this border, that is 17 or 61. Got it? So that is equivalence partitioning. So next, yeah, that's what is mentioned. So equivalence classes may be defined according to the following guidelines. If an input condition specifies a range, one valid and two invalid equivalences. Just now I told you, right? So if, let us take for example, a form accepts the age in between 18 to 60. Okay. Now what happens? So the valid class will be what? Let's say 30. Invalid class is what? 17 and 8 is 61. Okay, that's what. Next we talk about the boundary value analysis. Okay, BVA we say sometimes, boundary value analysis. So number of errors tend to occur at the boundaries of the input domain rather than in the center. So boundary value analysis leads to a selection of test cases that exercise bounding values. So BVA leads to the selection of test cases at the edges of class rather than focusing solely on input conditions. So BVA derives test cases from the output domain as well. So how do I create BVA test cases? If an input condition specifies a range bounded by values A and B, test cases should be designed with the values A and B, and just above and just below A and B. So if an input condition specifies a number of values, test cases should be developed that exercise the minimum and maximum numbers. So values just above and below the minimum and maximum are also tested. Let us say, yeah, now we apply. So basically, what it is saying is the boundary value analysis will focus on testing the values at the boundaries, like just below or just at or just and just above minimum and maximum values kind of thing. Okay. So let us say, for example, if input range is 1 to 100, let us say. So then we test with 0, 1, 2, let us say 99, 100, 101, like this. So for example, if an array will store 100 entries, so we tested 99, 100 and 101. So why do we do that? This makes us to see how it handles the near the limit. That's what boundary value analysis is. Next, orthogonal array testing. And before this, in boundary value analysis for the output and data structures, we apply this boundary value analysis not only to the inputs but also to the outputs and internal data structures like arrays, tables, and lists. Okay. Suppose let us say if a system generates a temperature versus pressure report with maximum 500 rows, we test with 499, 500, and 501 entries. Okay. Thing is, always test around the maximum capacity of the system so that we'll know it. Okay. That is about boundary value analysis. Now we talk about orthogonal array testing. So the orthogonal array testing is used when the system has multiple input combinations. Okay, so it helps us in testing more efficiently, like without checking every single combination. Okay, the orthogonal array testing method is particularly useful in finding errors associated with region faults, an error category associated with faulty logic within a software component. So to illustrate the difference between orthogonal array testing and more conventional one input item at a time approaches, so consider a system that has three input items called X, Y, Z. Okay, so now each of these input items has three discrete values associated with. There are 33 is equal to 27 possible test cases. Okay, so the FUDCA suggests a geometric view of the possible test cases associated with X, Y, and Z illustrated in figure. Referring to the figure, one input item at a time may be varied in the sequence along each input axis. So this result in relatively limited coverage of the input domain. Okay, this is represented by the left hand cube in the figure. Okay, let us see that now. So what we are trying to understand is, let me write here the earlier example in the previous slide. I will continue here. So the inputs are what? X, Y, Z. Okay. Now, so each has three values, right? So normally what? 27 combinations. When I say 27 combinations, that is of 3 into 3 into 3. Clear? So now we use this L9 orthogonal array. We test only 9 strategically chosen cases here. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Those are only the chosen cases. Okay. So referring to the figure, okay, where the left cube will represent you the limited test coverage and the right cube, that is orthogonal array, shows the broader and smarter coverage. Okay, so basically in our black box testing we don't look at the code, so we focus on what the system should do. Okay, like techniques like this equivalence partitioning or boundary value analysis and orthogonal array, all these will help us to create effective test cases and save time and ensure quality. That's it, friends. Thank you.